today we really start with this part that everybody talks about passive house. It's this opaque building envelope. Okay, everybody speaks as well about the windows and how expensive they are, and that it's causing overheating and blah, blah, blah. There's a lot in it. But the main thing that everybody talks about is this building components, the walls, the roof, the grounds. Do I put thermal insulation below? Do I not put thermal insulation below the slab? How thick is the insulation? It's far too expensive because we need to put so much more insulation in. But we'll cover that today. But before we start the day, I would like to review a little bit yesterday, and I want to make sure that we're all on the same page and that we know what actually happened. Did we learn anything yesterday? Did it empower you to realize that you are in the building industry? You're in the building industry, in the industry that has the biggest impact on the change, like the environmental changes that are happening. But this means as well, we can make a difference. And when we look to the economics, we have seen that we have the cheapest CO2 tons to cut down. And the beauty of it is as well, we're able to create these healthy outcomes. But let me put that all together of what you actually learned yesterday. So first of all, you learned about your first impression. Yeah, that's how we started the whole day, with the first impression. And I think it's something that is really, really helpful for yourself to have a little bit of feedback on that. I found it really, really powerful, this tool. That's the reason we put it in there. Might be not so passive house related, but we think it's not all about passive house, our lives, even it felt like that the last few months. Then you learned about SPA, and that we want to leave this place a little bit better than we found it. That's the mission of the company. That's what we do. And we're always thinking about how could we actually do it better, make it better, and improve and improve and improve it. And then as well, we gave you our why, our what, and how we actually do that. That's our philosophy of Smart Plus Academy, what we are doing. And you're having now this SPA experience, what is not maybe always too relaxing, but we're really looking after you and making sure you are served by us and that you're getting all what you can expect from us. Then you learned about the Passive House Institute. Yeah, and how it was founded and how it was developed and how it spread around the world like a positive virus. And the first Passive House project from the 1990s, like Wolfgang Feist built that for himself, his family home, and how that is still performing today. Yeah, and it's still showing us what is actually possible. Then as well, you learned about the Passive House standard and how the Passive House standard is an evolving standard. And then we can expect in the next 2 years a new PHPP coming out. And I guess that will involve as well some standard changes, because 2015, that was when this new standard came out, PHPP 9. There were a lot of changes to the standard. It has been developed in a completely new understanding where the fossil fuel industry is not benefiting any longer of the calculations, because that's what has been happening before, and they changed that, so it's now neutral or far more neutral than before. And then you learned about the Passive House standard. Yeah, so how is the Passive House standard defined? So the Passive House standard, yeah, we spoke about heat. Yeah, we spoke about the cool season and how we actually handle the cold season. So heating, what's the part in the standard regarding heating? What's the heating demand? Or what is demand, first of all? So we probably have to talk about what demand actually means. And the demand is the energy that is needed over a period of time. Yeah, so that's the amount of energy over a period of time. That's the demand. And then the demand is given in kilowatt hours. That's what the demand is. So what is the Passive House standard saying? What's the heating demand? The heating demand that we are allowed to have?
Not more than 15 per year.
15 what?
Not more than 15 kilowatt hours per annum.
Kilowatt hours per square meter per annum. So why do we break our values always down to the square meters? Why do we do that?
To compare.
To compare, exactly. Because if you're not breaking it down to the square meter, we can't compare a tiny home to a swimming pool. like an indoor swimming pool. But by breaking it down to the square meters, we can actually compare the values, and it gives us an idea how efficient that building is. And that's really the reason why we actually break it down to the demand. Yeah, so that's the demand. And then, yeah, it's an or requirement. We can have the heating demand, or what's the other part that we can look at? The heating
Load.
load. Yeah, load. And the load is now in watts, given in watts, and load is a point in time. Yeah, so to lift 5 kilos, I need to have the strength of lifting 5 kilos. Yeah, and I need it today or tomorrow or whatever. And the heaviest load that I can lift is then our load. Yeah, so the word gives it away again a little bit. So the load is calculated in watts. And what's the maximum load we are allowed to have? The heating load? 10 watts per meter square. And you see it's again, the meter square is in there. And the meter square is TFA, the treated floor area. Just put that in because of a part I want to show you today. I haven't showed you that yet, but explain it shortly today in this review and preview, and then we go into, we will learn that over the course of it, but I want to put it in there today. Then we have the cooling. The cooling side. On the cooling, we have as well the demand in kilowatt hours. Yeah, and the demand is again, that's the amount of energy that I need to pay for, or like that I need to deliver, or better said, heat that I have to take away, the coolness that I have to deliver to the building over a period of time. Yes, so again, demand is time. So normally we look at the annual or the months or the quarter, sometimes weeks, but normally it's always months, quarter, or annual heating demand. Yeah, and that's this A standing for here, the annual. Yeah, in the demand. And what is our demand for the cooling side? It's the same, yeah. Kilowatt hours per meter square annum. And then we're having here the OR requirement again. Yeah, here we're having again our load. And the load is again in watts. That's the strength, the maximum coolness that I need to prevent in point of time so that the bucket stays full. Yeah, you have a hole in a bucket. Yeah, and you have now a tap, and you open that tap to the maximum. And now the water that runs out of that bucket is the same water that runs into the bucket. That's the load. That's the amount of energy that I have to provide in a point in time. Soon I switch off the tap, then the level goes down, and for us, that would be temperature rising on the cooling side, or like dropping on the heating side. That's what that load represents. That's the amount of water, of heat or coolness that we can let out while the hole. So the hole is then the same size in that point in time, so that the level is not going up or down. So that's a 10 watts per meter square again. Yeah, and now on the cooling side, because it comes from a cool tempered climate, and often in Europe you're not putting cooling systems in, so they already put here on the cooling side the option for or a 10% overheating, 10% above 10%, like smaller than 10% above the 25 degrees Celsius. Well, that's now looking wrong from mathematical. 10% above, a maximum of 10% above 25 degrees Celsius. Yeah, so this, don't do it, guys. Don't do it. It's still in the standard. And that's the thing that I think, I strongly believe will be changed in the calculation, that it's actually calculated like heating degree hours, or it will be changed in the way it is expressed completely. I would like to see it as a 10% overheating as calculated as heating degree hours. Then I think it makes sense, but not the way it's done in the moment. Like 10% overheating would be 3 months having during the day temperatures above 25 degrees for 3 months. It's not acceptable. That part of the standard, don't just go for that part. Make sure that not happens. We gave you this table already, for how we look at overheating, and I show you in the software how to actually check your overheating issue. And as well on the cooling side, if you say I have no cooling, I have no heating, how do I go really passive, like a zero energy building without a heating and cooling system? I show you how to do that as well with the software. Yeah, good. So that is now the heating and cooling, and that is now the heat. Yeah, that's now the heat that needs to be delivered in the building, or the heat that needs to be moved out of the building. And now I'm putting here in blue our energy consumption. And now this is our bill. Here's our energy bill. Yeah, that's the bill that we're paying for. And now we're having an efficiency of that system, that is now delivering or removing that heat. Yeah, so this is now the standard tells us how much heat we are allowed to need and how much coolness we need. But now there is a system that delivers that, and that has an efficiency. Yeah, and that could be a heat pump with a COP. So then you need less energy. It could be an instant electrical system. Then it is more than what is here on the left, and that's that thing. And now what Passive House as well defines is now the end of that whole thing, and that's the primary energy. Yeah, so we're having the primary energy. The primary energy that they're defining is now here. We call that the source. Yeah, and there is the PE. That's the old standard before 2015. It still sometimes comes up in the exams, or has been coming up in the exams. I'm not sure if it will be still in your exam, because they're completely reviewing the whole exam thing now. Like the server is down until you're having your exam. So I hope that they're getting rid of that. And the PE, the primary energy that they're having here, that is still calculated differently than we're showing it to you now. Here they allowed 120 kilowatt hours per square meter and year. Yeah, and it tells us kilowatt hours. What is the PE? Primary energy demand. The hour gives it away that it is demand, and as well the annual, it's a time in there, so it's demand, yeah, not the load. And now here this square meter is not the same as this square meter. Yeah, so this is now something confusing, and I just point that out. That square meters here and this square meters are two different things. This square meters represents the area that is covered by the building, not the treated floor area, not the conditioned space. It's representing the area that the building is covering. I just let you know that square meter doesn't necessarily mean the same square meter. So that is a different square meter. Here it's TFA, and the other one is ground covering. Cover. Yeah, the same with the PER. There's primary energy renewable. So we're expecting that we're building in a completely renewable environment. Yeah, that everything is now renewable. And now we are only allowing 60 kilowatt hours per meter square annum. Between them, there is not really a difference. Yeah, there's not really a difference how much energy that we actually need. It's just a different way of calculating it. That is sometimes confusing. So if I'm now changing my software from and I just achieved the 120, and I change my software settings to PER, then the 120 more or less gets the 60. Yeah, it's just a different way of calculating it. Here they spoke about what the energy, what the source actually is. So is it coal? Is it no, they didn't say that. Like they actually said what type of energy is used. Is it electricity? Is it gas? Is it coal? So what is the energy source that you're needing? The PER is now actually looking at how is the energy used. Is it used for heating? Is it used for cooling? Is it used for dehumidification? Is it used for lighting, domestic hot water? So it's a different way of looking at it. Here they look at the electricity, for example. And now the problem with the electricity is produced out of gas, of coal, of oil, of nuclear, of renewable energies. And now they're all put together in one source. And now this is putting penalties on renewable energy because it pushes the fossil fuel, but that's just like going to another level, probably killing it now with you guys. But this is the reason why they changed it, because if you speak about the form of energy, like electricity, oil, gas, that is delivered to the house, then it creates a penalty for the renewables, and that's the reason it's calculated differently. So this is now our source. Yeah, and now we are looking normally only at this renewable situation now, and that is what the standard is defining for us. Yeah, and obviously now we're having here again efficiency, and that is now the PER factor, I think it's called. Yeah, and here is now this 1 for cooling, 1.7 for heating, 1.5 for dehumidification, 1.3 for hot water, or whatever that is. It's climate dependent. These are just reasonable numbers. Yeah, so that's the standard. Did that make sense? Could you follow that logic? The thing is, like, if you think about the amount of energy in a kilogram of coal, and how much of that energy of that is in that coal is actually arriving at the house is really, really limited. Okay. Yeah, that's the reason why it's twice as much, because you're getting a lot of heat out of 1 kilogram of coal, but this is never reaching your house, that heat, that kilowatt hours in electricity. Yeah, like that, like you're creating. So first of all, you have to dig it out of the ground. You're losing energy because you have that process. Then you're burning it, so you're creating heat. So we're having a burning process. What is then a lot of heat again? We're having there from heat to mechanical movement. So we're moving like a turbine with the steam that we're creating in there. It's another massive loss of energy from heat to a mechanical movement. And then that mechanical movement is then moved to electricity. Yeah, we have a turbine turning, and that turbine is then creating electricity. So we have heat generation, then mechanical movement generation. Out of the movement, we're creating electricity. So each step of the transform of energy, we're losing energy as heat normally, or in noise. Yeah, that's the reason they're noisy. That's the reason there's a lot of steam coming out. And that energy that was in the coal is not delivered to the house. And then we put it into the electrical grid. And now you know that these cables are getting as well warm. So we're having, again, a heat loss on the transport. And as well, if you're standing underneath this really high voltage systems, you hear that sizzling as well. So it's a noise. It's another loss. So we're having this loss again. And that's the reason there's so many losses from the coal until I'm actually, like, I'm burning coal, creating mechanical movement, creating electricity, put it through the whole country, bring it into my house, create again out of it heat, if you do instant heat generation. And now there's only a third of that energy actually arriving. Can you see that? Yeah. So that's the reason. With renewable energies, I put a wind turbine on the roof. I put up a wind turbine, and the energy is directly created out of that movement with an electrical engine. Yeah, that is moving out of this movement into electricity. So it's one transformation, and there's no losses, because, like, we can never get 100% of the wind movement forced out. Otherwise, we wouldn't have wind any longer on the planet. That would be weird. So it takes that energy out, and we're saying that energy that arrives at the rotor and is taken out of the rotor into the engine, that is now our available energy. And that's the reason the factor is normally 1. With fossil stuff, the factor, like, the efficiency is at 30% or something. Yeah, and then if you're then taking solar is even on your roof often of the times. You're producing energy on the roof, and the roof is and the energy goes directly in your house, so the efficiency is again 1. Yeah, so it's a bigger concept here. But this is now the energy concept of the Passive House standard, but there's one thing that is missing from the standard. Which one is that?
Air tightness.
The air tightness, the quality control, exactly. So we have the air tightness, and here the air tightness is a quality control, and we say that the building envelope only is allowed to have an air exchange rate per hour of 0.6. That's the quality control. You can write it as well with 1 divided by h, or you can write it as well with h minus 1. Yeah, they pretty much express all the same. Good. So that is the Passive House standard that we just went through. So this is the part that we learned really early on yesterday, or that we covered. Probably didn't learn it yet, but we covered it. So, and then after that, we went into the health part. Yeah, we start to speak about health, and we understood that our body temperature is 37 degrees Celsius. Yeah, so our body temperature is 30 degrees Celsius of all us humans, around that plus minus 0.3 degrees. That's our core temperature that we always have. And that's the reason why our comfort zone is climate independent between 20 and 25 degrees and a relative humidity of 30 to 60%. And in that comfort zone, 92% of the population is comfortable in that comfort zone. So you could set the temperature at 22 or 23 degrees. And if you take the whole population in there, 8% will say, I'm not comfortable. Probably half of them are saying it's too hot. The other half is saying it's too cold. Yeah, at that 22, 23 degrees. So that's the reason we say like 92% of the population is happy there. And for this other 8%, maybe we need to make it a little bit cooler, rather 19 to 24, or maybe rather 21 to 26. But that is now really like on the client's level. Yeah, it's a different one again. Then, but this comfort zone is strongly dependent on your clothing factor. Yeah, like if you're running around naked, you want it warmer than if you're wearing your skiing suit. Then you want it colder. So it's clothing factor dependent and activity dependent. If you're sitting, you have a less metabolic rate, and if you're standing or running, obviously you have a higher metabolic rate. So it's dependent on this as well, and we need to put that into consideration in our design. Then we looked at the global level from health, and we understand that Passive House can really prevent deaths in the extreme weather events. So when there's a power blackout, and we're having extremely high or low temperatures, then people die. We know that these numbers are pretty high, and this could be prevented by high-performing buildings like Passive House. And as well, it helps with the asthma levels and respiratory diseases that we're having globally. So we should really look at that. That is already bringing it to the local level. Like when we speak about public health spending, yeah, we know that in Australia, we're spending $5,000 per person on respiratory diseases. Yeah, this is not all building related, not all of them. How big that impact is, we can't really put in figures, but from former clients I'm speaking with, not all passive houses, but high performing buildings, they tell me like crazy stories, like they've always had like asthma, they had sinuses affections and all that stuff, and that stuff is gone in that houses. Yeah, or like it's far less with that. And we see that with allergies, we see that with these respiratory diseases, we see this asthma. So it really has a strong impact on public health spending. And then we came to the home level, and we understood that comfort is health. First, it's comfortable, then it starts to be uncomfortable, then it starts to be unhealthy, then it starts to be a health risk, and then it kills us eventually. And that's the reason why comfort is health, and that our sensors tell us if everything is fine, and that's the feeling of comfort. Yeah, so if you're feeling comfortable, then our body sensors tell us the body is not under stress. Yeah, and that's what we actually use for comfort. That's the reason why comfort is a health requirement. And then we spoke about the comfort thermal difference, that it can be a maximum of 4.2 Kelvin between the surface and the operational temperature, because otherwise we have this radiation effect of our body is then radiating to that colder surface, and that gives an uncomfort feeling. And as well, if the temperatures are higher, like the thermal difference is higher, we're starting to have a draft inside the building, and we have this draft effect without infiltration from the outside. Then we spoke about the mold issue, that normally occurs at 12.6 degrees. Do you remember why 12.6 degrees?
Because of the relative humidity, 80%.
The 80% relative humidity. If the starting parameters was 20 degrees and 50% relative humidity. So this is the reason I don't like the 12.6 degrees measurement. I normally like to really use the 80% relative humidity on the surface, because that is the issue. In hot climate, I would even put it to 70% relative humidity, because higher temperature, quicker mold growth. Yeah, so that's the reason in hot climates I'd rather have it higher, I'd rather have a higher safety, so a lower relative humidity. So I would, in hot climates, rather use 70% than 80%. And then we have the condensation figure, the 9.3 degrees Celsius. That's when the relative humidity reaches 100%. In other words, it reaches dew point, and then we have condensation. And that is not necessarily a health issue. It's more a structural issue, that your structure starts to rot, that your structure starts to rust. Your carbonization of your concrete starts to go up and up and up, and all that. Like it's more like a durability issue, the condensation. And obviously, when we have condensation, we have as well mold problems, but we have that even before we have condensation. And all this you learned in that course, how to handle and how to control that, and how to actually come to these figures. Then we looked to the sustainability. We looked at the sustainability situation, and we understand that our industry is the biggest, has the biggest potential to stop climate change. And I think I should let us feel in a way as well proud that every minute that we are spending on our job, if we are applying what we're learning here, we're actually fighting climate change. Yeah, so this is the message of the sustainability. We learned that the available energy in the different regions is as well really shows a relation to the social development of that regions. And out of that, we can conclude that we really need to produce far, far more energy than we are producing right now to help poor regions of the world, so that they can come to the same living standard like us. But we can only do that in a sustainable way. We can't do that with fossil fuel. We know that the sun, I didn't put that figures out yesterday, but we know that the sun is giving us 10,000 times the energy that we actually need. So we only need to harvest a 10,000th time of that energy to actually cover the energy need right now. If you go 10 times, then everybody on the planet could more or less live like us. From an energy perspective, not necessarily from a resources perspective. That's another one when we're speaking about batteries, about like all these metals and minerals that are not that rather rare. We have to find other solutions for that. But generally, from an energy perspective, I don't see a big issue. We know right now with our fossil fuel-based economy, we're putting 15.5 kilograms of CO2 into the atmosphere in average. Here in Australia, it's rather our body weight or twice our body weight every single day. And we learned that renewable energies are actually cheaper than fossil fuel. Yeah, they only have a storage issues, but we as well have found storage solutions with the energy vault, with the heliotherm, and we even have technologies for carbon capture, so reversing climate change without tampering, like without climate tampering, like putting I think it's phosphor into the atmosphere to then have a reflection layer in the sky, and then changing, like fighting climate change with tampering with the climate really in local levels. Super dangerous, because there might be a beneficial effect at this location, but a negative effect on a different location. Now let us not go there. So carbon capture is something we can do without political issues. We have solutions for storage. We have solutions for the heat production, for producing steel and concrete in a sustainable way. All that is existing. The technology is there, and I'm looking into the future really, really positive regard that. And as well, I showed you a little bit of calculation that even because often when we see that big numbers and say, what can I as a single person do if I'm doing just one project a year, how is that making a difference? If you build one passive house a year and your passive house project is just inspiring other 2 people per year to build a passive house, you're building thousands, and you do that for 10 years. So you build yourself 10 passive houses every single year. You inspired more than 1,000 passive houses just with this growth of 2. And this is the reason if we work together, we can really make a difference to the sustainability, to the health of the population. And this is even economical. So we went into the economical part. We learned that that climate change, that we can actually fight climate change, because if we are able to spend the same amount of money on fighting a little thing like called a virus to get rid of that, and I'm pretty sure we handle that nicely over the next 2 years. It's pretty annoying being in lockdown, but that's temporary. So if we're able to fight a virus, then we're able to fight climate change as well. The financial resources are there. So it's just a question of will, and it will happen. So I'm really positive on that. Passive house or high performing buildings will have a really strong part in that. I showed you that as well with battery storage and seasonal storage and all that things, how they're related to each other. We know that the additional costs for passive house are usually between $200 and $750 per square meter. Up to 20% is what is normally said. When we look to Australian figures and compare them with European figures, the average is normally between 7 and 8%. So when we look at different passive house projects in Australia and we look to different passive house projects in Europe, we come to same results already. What I think is a massive achievement for the Australian building industry, because we're new to it. Then studies show that the architectural features are actually costing 30% without helping the performance. So architectural features like glazed handrails and toughened glazed balconies and stainless steel handrails and a bathtub for $10,000 instead of the one for 50. And all that things, they're architectural features. They're 30% of the costs. They can make the house look far nicer, but I think there's far more cost-effective ways of making houses look nicer than spending 30% on top of the building costs. Then after that, we went into passive house design, and we realized that passive house is really a team play, and we have to rethink the design process, that we're getting the builders, the engineers, the electricians, everybody involved in the design project, especially here in Australia, because sadly, the pricing of projects, the understanding of construction in the design environment is not that high, and builders have a far better understanding how to cut costs. So get their knowledge, especially the builder's knowledge, into your design process. They look at it and they say, here, if you change that, I can cut off $50,000. So get them involved, and don't show your design to your client before you know it's in their budget. Then we learned that size is the biggest driver for cost, sustainability, and running costs, like building costs, running costs, sustainability, and affordability. We learned that shape is the second one, and then the compactness of the building is the third one. And then we went to this crazy attempt to come from climate to lambda. So we started with climate change, and when they ended up with a material characteristic lambda, the thermal conductivity of a material, we went from the material characteristic lambda, came from climate, we came from the other side. So we came from the big picture and we went smaller, and we understood that we are calculating our source energy. We understood that we are calculated the energy that we're paying the bill for. Then we actually looked at the energy that we need to deliver as heat or remove as heat in the building. Then we calculated how that losses happen through the building envelope, our U value calculation, thermal bridge calculations. And then we learned that the U value is just the reverse of the R value. And then we came from the R value that is related to the lambda value. And then we came there. So that's pretty much what we've done yesterday. So did we learn something yesterday? Yeah, it's a bit crazy when we just review it this way. But I think it gives you an idea of what happened. So today we speak about that building envelope. Yeah, we speak about the biggest component of the passive house, the one that makes the biggest difference, our box that we're building. Yeah, pretty much. Yeah, that's the part that we're talking about today, how to do it, how to calculate it, and how all that things are related to each other, from thermal insulation, thermal bridging, air tightness, vapor control, and we'll see today how that build-ups would look in any climate with any building material. Yeah, so that's what we're doing today.